Why, hello everybody. Today we're going to do section 13.6, which deals with cylinders and quadric surfaces. Actually, what we're going to be doing is learning how to do 3D graphs. So let's get started. Now, I did copy a definition, but at this point when we read it, it's not going to mean a whole lot to you. It says definition: a cylinder is a surface that consists of all lines called rulings that are parallel to a given line and pass through a given plane curve. And right now when you read that, you're like, what on earth are they talking about? Well, we'll see in a second what we're going to talk about. In our case, we're going to have a graph that's called a cylinder when the equation only has two variables in it, be it xy, yz, or xe. It will be lacking one variable. Now let me give you an example of what we call a cylinder. We want to graph the equation z equals x squared in 3D. Okay, in 3D. Now, before we do anything in 3D, let's go back and revisit 2D, all right? In two-dimensional space, if I had a z-axis and an x-axis, and I wanted to graph the equation z equals x squared, I hope and pray most of you would know what that graph looks like, right? It's a parabola. It's going to be an up-z, right? And it's going to look like this. Now, that's in two-dimensional space. Okay, in the space that has just an x-axis and a z-axis on my piece of paper. All right? Well, in 3D, if I let y be 0, here's the x-axis, here's the z-axis, and this is the positive y-axis, I'm going to sketch the equation z equals x squared. You all with me? Z equals x squared is going to look just like this. It's positive z. And notice on this side I have the z equals x squared, and to show that I'm going behind the yz plane, I'm going to make a little dotted line. Now this is on the xz plane. Remember, on the xz plane, what's your y coordinate equal to? 0. Okay, so we're taking our y coordinate equal to 0. So on all of any point that's on here, if I wanted to put the coordinates of the point, the y coordinate is 0. And maybe this one, maybe x is 2. And if x is 2, since z is 2 squared, it would be 4. And maybe back here, x is negative 2. And z would be 4. And the origin works too. 0, 0, 0 works, right? And we could also have another point right here. Maybe 1, 0, 1, since 1 squared. And back over here, this might be negative 1, 0, 1. And so we have some points. Now, going back, let's go back to your old Algebra 1 days. Remember when you did the graph of like y equals 2? Remember when you did that? And you said, oh yeah, here on the y-axis is 2. And some of you would put a dot there, and then the teacher would go, no, 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 that's not the whole graph, right? And you go, well, y is 2. I have my dot of y equal 2 there. And she'd say, but remember, x is not in the equation. So since x is not in the equation, you could let x be anything. Remember that? And we could say x could be 1, in which case the point 1, 2 would work. Or x could be 2, the point 2, 2 would work. Or x could be negative 1, the point negative 1, 2 would work. And so we would go parallel to the x-axis, right? We would go parallel to the x-axis, and we would have that entire line would be the graph of y equals 2. And so we went to y equals 2, but then since x could be anything, we went parallel to the x-axis to the left and to the right and generated that whole line. Okay, you with me? This is the same thing here. All of these points worked. So since y is not in the equation, y could be anything. And so what we can do is we can take any point in the xz plane and move it parallel to the y-axis, give it a different y coordinate. When we do that, we get what your book calls as rulings. Because when we go parallel to the y-axis, we're going to be drawing lines parallel to the y-axis. Are you with me? So if this point works, 0, 0, 0, 0, 0 works, any point along the y-axis, if I go parallel to the y-axis, will also work. Look, this point right here could be maybe 0, 0, 5. Excuse me, 0, 5, 0, right? Because I moved over along the y-axis 5 units. Now, since I can take any point and move it parallel to the y-axis, what I prefer to do is think of this entire sketch in the xz plane. And since y can be anything, I can think of this as you have a string and you've sprayed it with spray starch and it's nice and stiff, and I'm going to drag it parallel to the y-axis. And when I do that, think of another another XZ axis right here. Here is your line. Here's your parabola. And all of these points got dragged, all of these points got dragged, all of these points got dragged. And can you picture it? What you have is a surface. So when you have an equation that is missing one variable, draw it in the plane, like in this case in the XZ plane, and then think of dragging it parallel to the axis that's not in the equation. As you can see, what you're doing is you're moving this point parallel to the y-axis, this point parallel to the y-axis, this point parallel to the y-axis, and what you're getting is this surface. Now, those of you that are on campus or have access to one of the campuses, it's sort of helpful actually to have Maple do the sketches for you also. So what I'd like to do is I'd like to have Maple draw the graph of z equals x squared. So right now I'm going to go to my computer. I'm not going to do this for every single one. But those of you, if you're in the math lab here at Stanton campus, or be it at the Terry campus or at the Georgetown campus, and you have access to Maple, or some of you even bought it and put it on your computers, when you're trying to sketch these, sketch them and then take a minute and put them in Maple and look at it to see what Maple gives you. Now, I already took the liberty of loading Maple because sometimes it takes a little bit of time to load. All right, but first of all, this is a 3D graph. So on Maple, to be able to do 3D graphs, what I have to do is I have to type the command with parentheses plots, be nice to spell it right, 3D close parentheses semicolon. With plots 3D, and it tells me invalid. So let's go back to just how about with plots. Now, as you can see, it's loading, and it's listing all of the many commands that I have opened by typing with plots. And if you notice, one of the commands that I have opened, and let me just highlight it right here for you, is plot 3D. Point plot with plots. I'm looking for plot. Oh, implicit plot 3D is right here. Implicit plot 3D. Now I'm going to use implicit plot 3D today. All right, so coming down here, I'm going to tell it to implicit plot 3D. But my caps are on. Let's turn them off. I am PLICIT PLOT 3D. Parentheses, and now I need my equation, and my equation is just z equals x squared. And now the problem with implicit plot 3D is I have to give it a window for the x coordinates, the y coordinates, and the z coordinates. So I'm going to let x equal, how about -2 to 2, -2 dot 2. That means I'm going from -2 to 2, comma, y goes from, why don't we let it go from -3 to 3. And since z is equal to x squared, I'm going to have my z go from, it's always positive, so how about -1 to 4? Let's see how that works. Let's hit enter. And what it's doing the graph of z equals x squared for me right now. Here's my graph. Now if I click on the graph, Maple by default does not put any axes. But if you look right along here, you see these little red dots here? They give you different axes. If I click on this one, it gives me an axis like a box around the curve. I sort of like this one that goes inside. Okay, this is my x-axis coming. It comes out just like in the normal way. X coming out at you, y going to the right. So let's do this one. Along here is my x-axis. This is my x-axis going this way. So from the center, it's coming out this much. The y is coming down this way, and z is coming up. And notice you can click on the graph, and you can actually move it. And you can see it looks like a little sheet. As you can see, you took your parabola, z equals x squared, and you drug it along the y-axis, and you're dragging it along parallel to the y-axis, and you're getting almost like a sheet, and it's called a cylinder. Okay, let's do another one. Next one I want to look at is x squared plus y squared equals 25. Now before we do that one, back in your old Algebra 2 days, what's the graph of x squared plus y squared equals 25 look in 2D? If I just draw it in the xy plane, it's a what? It's a circle, yeah. X squared plus y squared equals r squared is a circle, right? Circle of radius 5. So it's a circle of radius 5. That looks pretty good. So what I'm going to do back here is I'm going to draw a circle in the xy plane that has a radius 5. So you can go to the right 5, 1, 2, 3, 4, 5, to the left 5, 1, 2, 3, 4, 5, come around here. And this is showing that it's going back and coming around. And as you can see, I'm not the best drawer in the world. Okay, but it's a circle. Let's make it a little bit better. There you go. It's in the XY plane. I draw it in the XY plane to begin with. Now, what coordinate's not in there? Z. Z is not in there. And so what we're going to do is we're going to take this curve and we're going to drag it parallel to the Z axis. So this thing's in spray starch. I'm going to drag it parallel to the Z axis. And as you can see, definitely I would call that a cylinder, huh? A cylinder looking like a Campbell soup can. Okay, and as you can see, it's going around like that. And also, it goes infinitely down too, but you can't draw it forever. Isn't that cool? Okay, let's do another one. Okay, next one I want to look at is, how about y equals z squared? So I say to myself, okay, now if I was doing y equals z squared, just in the yz plane, here's the y-axis, here's the z-axis. Notice y equals z squared. Y is always positive, right? Z can be positive and negative, but since y is z squared, y is positive. So that's going to look something like that. You all with me? So I'm going to go back over here, and I'm going to draw y equal, now this is x, this is y, this is z. And I'm going to draw, now, positives up here, but negative I'm going to do dotted because it's below the xy plane. Can we all see that? This is the curve y equals z squared. What coordinate's not showing? X is not showing, so we're going to drag this along the x-axis. Okay, now what I like to do is I like to actually draw my yz axis down here a bit. And since I'm dragging this curve down here, I actually replicate it down here. And then I realize that this point's being drugged to here, this is getting drugged to here, this point's getting drugged to here. And can you see the sheet? Can you see the sheet? It's this curve, it's coming around like this and coming around like that. Okay, and this is called a cylinder. Whenever your equation only has two variables in it, it's called a cylinder. Okay, let's do another one. X plus y equals 5. So I'm going to draw the line x plus y equals 5 in the xy plane. Now if I go back to 2D about that, how do you do the line x plus y equals 5? That's a what? It's a line, right? It's a line. The quick and dirty way would be get two intercepts if we could, you know. So my two intercepts would be 5, 0 and 0, 5. Okay? So in 3D, I'm going to have 5, 0, 0. I draw it in the xy plane. 1, 2, 3, 4, 5. So that's the point 5, 0, 0, because we're letting z be 0 also. And then we want the point 1, 2, 3, 4, 5. 0 in the x direction, 0, 5 in the y direction, and 0 in the z. And here's my line. Now notice this line does go forever. Okay, but I'm just drawing it in the first octant. And then since z's not showing, I'm going to draw this line. I'm going to pull it parallel up to the z-axis. Now notice what I like to do is I like to draw a similar axis parallel to the x-axis, draw your line right there, and then just show that you're pulling it up. And can you see what you're getting there? What am I getting? A plane, huh? I'm getting a plane. Isn't that cool? I think this is fun. You definitely have to practice at the drawing. And do I give you on the test things to draw? Yes. Okay. Okay, let's do another one. Oh, I want to review a little bit before. Going back, we talked about this in a minute. There's three conic sections from 2D that you really have to know in order to do some interesting shapes in the Calc 3. The first one is, you already told me that, that's a circle. That's a circle. It's an equation of a circle. It's a circle of radius r. So it's going to be up r to the left r to the right r down r. And that's a graph of a circle. Now sometimes we could weight the coefficient of x squared, the coefficient of y squared, in which case, and I'm going to be assuming a, b, and c are positive quantities. If a, b, and c are positive and you get some positive number times x squared plus some positive number times y squared equals some positive number, it's going to look sort of like a circle, but it's going to be a little bit flattened, and we call that an ellipse. Okay, do you remember that? And in particular, let's look at a couple of ellipses. The equation x squared over 9 plus y squared over 16 equals 1. Notice you could look at that as 1/9 x squared plus 1/16 y squared equals 1. So it's positive number times x squared plus positive number times y squared equals some positive number. That is an ellipse. you can actually figure out where it's crossing the x-axis and where it's crossing the y-axis. And this isn't absolutely essential every time we do our sketches in Calc 3, but notice if I let y be 0, I get x squared over 9 equals 1. Well, that would give me x squared is 9, or x is what? Plus or minus 3. So we can go plus 3 minus 3. And if I let x be 0, that means I'm along the y-axis, I get y squared over 16 is 1. So what's y? Plus or minus 4. 1, 2, 3, up 4. 1, 2, 3, 4. And here's my ellipse. Okay? So when you have positive x squared plus positive y squared equals positive number, you have an ellipse. In this particular case, you have 2x squared plus 3y squared equals 6. If we divide by 6 throughout, that gives me, let me just put this on a sheet of paper right here, that gives me x squared over 3 plus y squared over 2 is equal to 1. All right? And if we let y be 0, you're going to get x squared over 3 is 1, or x is going to be plus or minus square root of 3. And if I let x be 0, I'm going to get y squared over 2 is equal to 1, or y is plus or minus square root of 2. So my x-intercepts are going to be plus or minus square root of 3, and my y-intercepts are plus or minus square root of 2. And again, it's going to be a little bit wider along the x-axis and look like that. Okay? Now, if I take this exact same equation but just change the plus to a minus, we get a hyperbola. Okay? Now the thing to, now we're going to go wacko on the hyperbolas, but your equation could look like this, or your equation could also look like ay squared minus bx squared equals c. You could have, but now, remember I'm assuming a, b, and c are positive. If it looks like this, just remembering back from your Algebra 2 days, if x comes first, your hyperbola is going to be crossing the x-axis. If x comes first, you're crossing the x-axis. If y comes first, what do you think you're going to be doing? You're going to be crossing the y-axis. Okay, so it's just something to remember. Now, here's an exact one. Y squared over 16 minus x squared over 9 equals 1. Since y comes first, what axis are we crossing? The y-axis, right? That's what we said. Since y comes first, we're going to cross the y-axis. Notice I'm not deriving any of this. I'm just sort of reviewing real quick. Notice, if you let x be 0 here, you get y squared over 16 is 1, or y is plus or minus 4. 1, 2, 3, 4. 1, 2, 3, 4. So that gives me 0 plus or minus 4, or 2 points. Now notice, if you let y be 0, you have a problem here, because if you let y be 0, you get minus x squared over 9 equals 1, or x squared equals negative 9. Could that happen? No, it cannot happen. And I'm not going to go back to the whole derivation of hyperbolas and what their definition is and all of that type of stuff, but a nice thing to know, if instead though, since what's underneath the, if I got rid of that minus sign, I would have x is plus or minus 3. What that is good for, and we're not going to do this too much in this class, but if you put that plus 3 minus 3 in there, and you made a box, you might remember this or not, if you draw the x that goes through the diagonals, through the origin, through the diagonals, what that box is a guideline for your hyperbola. We said y was coming first, so we were crossing the y-axis, and then those lines are your guide, they're like your asymptotes. And that's what my hyperbola looks like. In our class, the main thing is I want you to know it's a hyperbola and it's crossing the y-axis. Because you're going to be doing real down and dirty sketches is what you're going to be doing, not real exact. Okay? So on the flip side, if I had x squared over 16 minus y squared over 9 equals 1, that would be a hyperbola that crosses the x-axis. We're going to cross the x-axis. And if we let y be 0, we can see we get x squared over 16 is 1, or x is plus or minus 4. So we do have two very real points, 1, 2, 3, 4, 1, 2, 3, 4. Those are real points, so I make them nice and bold and dark. If we let x be 0, they're not real points. But as I can see, my y would be plus or minus 3, wouldn't it? So I'm going to do that in red because it doesn't really exist. And remember I said you can make this box that goes along here and down here. And your asymptotes go through the diagonals of the box. And my hyperbola is going to go through these points because he's crossing the x-axis, and these are my guidelines. Just a quick review on how you could do quick hyperbolas and ellipses back from your Algebra 2 days. Okay. Now I'm going to need these in a minute when I'm doing my graphs in three-dimensional space. So, big thing to remember, let's just talk real fast. If I had an equation that looked like 2x squared plus 3y squared equals 9, what's the graph of that going to be? With a plus. Ellipse. What if I had 2x squared minus 3y squared equals 9? What's that going to be? Hyperbola, isn't it? And a hyperbola, that crosses which axis? X. Okay? And if I instead wanted 3y squared minus 2x squared equals 9, that again would be a hyperbola, but it would be crossing the y-axis. Okay? All right. Now, this is just from your book, a little statement, and then we'll see what the heck it means. In order to sketch the graph of a surface in three-dimensional space, it is often useful to determine the curves of intersection of the surface with planes parallel to the coordinate planes. These curves are called traces. You're going, what are they talking about? Well, let me show you. Okay? Suppose I wanted to come up with the graph of x squared plus y squared over 9 plus z squared over 4 equals 1. I want to come up with the graph of that. All right, now what we're going to do, let's go back and look what that definition says about traces. It says we want to determine the curve of intersection of the surface with planes parallel to the coordinate planes. Let me show you what we're going to do. We're going to take our surface and we're going to slice it. We're going to cut it into multiple little slices and look what those slices look like. The first slices we're going to do are, I'm going to look at this surface and I'm going to try to get a picture of what this surface looks like. I'm going to look at this and I'm going to say, what if I just looked at the part of this surface that's on the xy plane? The part of the surface, now that would be taking the intersection of the surface with the xy plane. Now, you tell me, if I'm on the xy plane, what can you tell me about all the points that are on the xy plane? Z is 0, absolutely, Z is 0. So if I'm on the xy plane, Z is 0. Now, if z is 0, I'm going to plug a 0 in for z. Is that okay? And I have x squared plus y squared over 9 is equal to 1. Because if I'm in the xy plane, the z-coordinate is 0. Now, if the z-coordinate is 0, what is this graph of? What is that? It's an ellipse. That is an ellipse. And if I drew my ellipse in the xy plane, if y was 0, x would be plus or minus 1. And if I let x be 0, y would be plus or minus 3. And my ellipse would look something like that. So I'm going to go back here, and I'm going to say, okay, I'm going to first look at the, we'll put it on the side, the xy plane has z equal to 0. And if I have z equal to 0, I have x squared plus y squared over 9 equals 1, because z is 0. If I let y be 0, x is plus or minus 1. If I let x be 0, y is plus or minus 3. 1, 2, 3. And then we're going to go back here. 1, 2, 3. And I'm going to draw, I have this point, that point, that point. Dot it when it goes behind. And there's my ellipse in the xy plane. Now, is the xy plane important just by itself? No, 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 no. Why don't we now look at the yz plane? Looking at the yz plane, what's equal to 0 in the yz plane? If you're in the yz plane, what coordinate is 0? X. If you're in the yz plane, x is 0. And if x is 0, if I let x equal 0, I get y squared over 9 plus z squared over 4 equals 1. In the yz plane, what's that a graph of? An ellipse. That's an ellipse. And let's talk about the intercepts of that ellipse. If you let z be 0, y is going to be what? Plus or minus 3. And if you let y be 0, z is going to be plus or minus 2. Do you all see that? So if I let y be plus or minus 3, I already have that in the y, along the y-axis. But along the z-axis, I've got to go plus or minus 2. Up 2, down 2. And in the yz plane, I have dotted because I'm underneath, then solid, then dotted to go here, and then dotted to get back there. So I have an ellipse on the xy plane. I have an ellipse in the yz plane. While we're at it, why don't we do, the only thing we have left is what, the xz plane? Well, if I'm in the xz plane, y is 0. And if y is 0, I have x squared plus z squared over 4 is equal to 1. And so if I let z be 0, x would be plus or minus 1. And if I let x be 0, z is going to be plus or minus 2. So if I do 1 plus or minus 1 on the x-axis and plus or minus 2 on the z-axis and draw that, it's coming down like this, dot, 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 dot. Back through here and then up. Do you see what it looks like? What does it look like? It looks sort of like a football, okay, sort of. This is called an ellipsoid. It's called an ellipsoid. Let's put it on maple, because I think after we've done the sketch, I think it's going to help us to see what happens here. So popping it on maple. Popping it on maple, let's scroll down here. I'm going to put in implicit plot 3D, I-M-P-L-I-C-I-T, P-L-O-T 3D. And to make my life a little bit easier, I'm going to highlight this and copy it. So next time I need it, I don't have to type the whole thing. And my equation was, let's see what it was. It was x squared plus y squared divided by 9 plus z squared divided by 4 equals 1. Now, we already did some of this graphing. The x varied from 1 to 1, so I'm going to let x vary from -1 to 1. Y, when we did the sketch, varied from -3 to 3, so I'll go -3 dot dot 3. And z ranged from -2 to 2, so why don't I pick that? Did I have 2 dots? Oh, I have 3. That might be a problem. Let me go back. Thank you. I appreciate when I make a typo letting me know. Okay, 2 dots. And telling it to draw it. I'm going to click on it and tell it to put a little axis around it. And look at that. There is my ellipse. Looks like a sphere, but it's not a sphere because it's of length 2 in the x direction. In the y direction, it was of length 6, and in the z direction, it's of length 4. Isn't that cool? And all I'm doing is I'm pressing down on the left button on my mouse, and I'm just sort of like touching it and moving it. And this helps so much, you know, when you make a bizarre little sketch like I did and actually seeing in 3D what it looks like. Okay? All right, moving right along. Let's do another one. This one, Z, oh, by the way, if we look here, I just copied this, I had them print this out of the textbook. Looking right here on this one right here, this, by the way, this chart is very, very nice. You're allowed to use it when you're doing your homework, but I would try to conceptualize and figure out what it's going to look like. Notice they're telling you that if your equations any in the form of x squared over a squared plus y squared over b squared plus z squared over c squared equals 1, they tell you that this is going to be an ellipsoid. And you can see it's going to be a football. And as you can see with that equation, if the equation's in this form, if you let z be 0, if I let z be 0, I just get x squared over a squared plus y squared over b squared equals 1. That's an ellipse. So your xy trace in the xy plane will be an ellipse. If you let x be 0 in the yz plane, look what you're getting. Y squared over b squared plus z squared over c squared equals 1. What do you have? An ellipse. So this is your easiest graph to do. Okay, it's called an ellipsoid because every way you slice it, you've got an ellipse. Soid means you're in 3D. Okay, so the next one we want to do is z equals 4x squared plus y squared. Now this one, before you do anything, notice z equals something squared plus something squared. If you have something squared plus something squared, it's positive. Do you all see that? This is positive, that's positive, a positive plus a positive is positive. So I know my z is positive. So my graph is going to be positive z. Well, any point that you plot that has positive z's above the xy plane. Okay? Now, before, so I'm going to be I'm going to be above the xy plane. In the past, we sliced it and diced it. Okay, so I'm going to slice it and dice it this way. If I let z be 0, and I'm just looking at what's my slice in the xy plane, notice if I let z be 0, I get 4x squared plus y squared is 0. What coordinates would satisfy that equation in terms of x and y? X squared's positive or 0. Y squared's positive or 0. The way I can make this positive or 0 plus positive or 0 to add up 0, the only way that's going to happen is if I make both x and y be 0. Anything else, you're going to be bigger than 0. So when z is 0, the only point that works is x is 0, y is 0, z is 0. It's just the origin. Okay? Now why don't we try the xz plane? Why don't we let y be 0? If I let y be 0, y is 0, I'm in the xz plane, I get z equals 4x squared. What's that a graph of? Z equals 4x squared. We're doing this in the xz plane. Z plane, x plane. What does the graph z equals 4x squared looks like? That's a parabola, right? It's an up-z parabola, right? It's going to look like that. Okay, so in the xz plane, I'm going to graph this, and I just do dotted lines to show that I'm back here, the negative part of the xz plane for negative y's, or negative x's, excuse me. Now, while we're at it, we have one more to do. Let's do, I did y equals 0, I did z equals 0, so I'm left with x equals 0. If I let x equals 0, I'm now in the yz plane, and I get x is 0, z equals y squared. Again, in just the zy plane, that's a parabola. So over here in the yz plane, I'm going to have, it's a little bit steeper than, a little bit less steep. Let's do this, looking like that. Okay, so each slice is giving me a parabola. Now, before, with the ellipsoid, there was no reason for me to slice it with any other trace. With this one, what I want to do is, I want to cut it at certain heights. Now, if I cut it at a certain height, I want to slice it like z equals 5, z equals 10, z equals 8, right? At all the points at z equals 5, it's 5 units above the origin. So if I slice this, let's try it like at z equals, let's say 5. What do I get here? I get 5, because z is 5, equals 4x squared plus y squared. What's that a graph of? An ellipse. It's an ellipse. So if I slice it at z equals 5, what I'm getting here is an ellipse. Now if I slice it a little bit higher, maybe like z equals 10, I'm just going to get another ellipse, but it'll just be bigger. And do you see what this thing looks like? What does it look like? It's called, pardon? It's called an elliptic paraboloid, is what it's called. It's not a cone because it's not a sharp edge. Parabolas are smooth at the bottom. So it's called, and the reason it's a paraboloid because it's a parabola rotated around, but every time you slice it in the z direction, you've got yourself an elliptic paraboloid. Now notice, in this case, it's z equals something squared, x squared plus y squared. So it's moving up along the z-axis. If instead I had an equation that looked like x equals y squared plus z squared, which way is that paraboloid going to be going? It's going to be going along the x-axis. As you can see, x is going to be the guy that's always positive. This thing's going to be coming around like this. And each way you slice it for different values of x, you're going to get an ellipse coming around like that. And as you go out further and further and further, it's going to be bigger and bigger and bigger. Your book is very kind for option number 2. They have elliptic paraboloid, and they have the thing here. But you might want to put here, like if x is your odd, notice z here is your odd man out, so your paraboloid's moving up along the z-axis. If instead you had x equals y squared plus z squared, it would be going along the x-axis. Or if you had y equals x squared plus z squared, y was odd man out, you'd be going along the y-axis. But this is a lovely little chart to help you. Okay, the next one I want to look at, x squared over 9 plus y squared minus z squared over 4 equals 1. Okay? First of all, we're going to find a quick and dirty way to remember these, but right now I just want to do a couple little slices and dices to justify why it looks the way it does. Notice, if we let z be 0, in other words, I want to look at what is its trace on the xy plane. Okay? If z is 0 here, I get x squared over 9 plus y squared equals 1. And what is that? That's a what? An ellipse, right? An ellipse. That's why we reviewed these, because we're going to use them so much. It's an ellipse. This ellipse is crossing the x-axis at plus or minus 3, crossing the y-axis at plus or minus 1, if you really care. All right? But in the xy plane, 1, 2, 3, 1, 1, I've got this ellipse. Okay? Now, why don't we let y be 0? Okay? If I let y be 0, I'm in the xz plane. And if I let y be 0, I get x squared over 9 minus z squared over 4 equals 1. That's a what? Hyperbola. Hyperbola. And since x comes first, what axis is this hyperbola crossing? It's crossing the x-axis. So if I just drew it in the xz plane, it's going to be coming around looking like that. All right, now coming back here, I want to draw this in the xz plane. You told me it's crossing the x-axis. It's going to be coming around like this. And back here, it's going to be coming back and going down like that. Okay? Now, let's see. We did the xz plane with y equals 0. I guess we're going to try z equals 0. If I try z equals 0, no, I tried y equals 0. I did z equals 0. Now I have to do x equals 0. If I do x equals 0, I get y squared minus z squared over 4 equals 1. Notice I'm in the yz plane. And again, that is a hyperbola. It's a hyperbola that crosses the y-axis, because y comes first. So coming back here, here is the yz plane, yz plane, and it's going to be coming down here, and we're going to have a hyperbola that's coming around like this. Okay, yz, it's coming down, cross it. Wait a second. We had x equal to 0. Yeah, and we're going to be crossing the yz plane. Okay, now I want to do one more thing. Let's notice the odd man out. Who's the odd man out on this equation? Oh, wait a minute, I don't like something I did here. Let me come back here and look at this for a second. Where did I do with that one sheet? We let y be 0, and we're okay. We're crossing the x-axis. That's okay. We let y be 0. We're crossing the, that's fine. Okay, but now, what I want to do, looking at this, let's look at this. Okay, looking at that. Okay, looking at that. Let's let z equal various positive numbers. Okay, in fact, let me come back here and regroup what we had here so far. We have x, y, z. We let z be 0, and we had ourselves an ellipse. Okay. In the xz plane, we have a hyperbola. And it come down like that. In the yz plane, we had another hyperbola. It's coming down like this. My picture's not so good. Now I want to say when I move up here, what's happening is I slice it along the z-axis at various heights. Okay, now I'm letting z equal various numbers. Suppose I let z be like a 1 or a 2 or a 3. Do you see this number right here is a positive number? And if that number is a positive number, what is this? What is the graph of x squared over 9 plus y squared equals some positive number? What is it a graph of? A what? An ellipse. So if I go and I want to slice this graph at various heights, like at z equals 5, what I'm getting here across the top is as an ellipse. Or if I slice it down here down the bottom, I'm getting an ellipse. Do you see what this graph looks like? It looks like this tube. You see the tube? It looks like a tube. Now the easiest way to remember this is if you have the equation, you see you have an x squared, a y squared, a z squared, and a positive number on the outside here. By the way, this is called a hyperbolic paraboloid. A hyperboloid of one sheet. As you can see, when I cut it, I have hyperbolas in various directions. But as I cut it this way, I'm getting ellipses. It's one sheet because it's going up as one sheet. Now coming back here, notice I have x squared plus y squared minus z squared. This gives me a hyperbola. This gives me a hyperbola. And we have one minus sign. When you have one minus sign, that's going to tell you that you have one sheet. Also notice your minus sign here is with the z, and notice this graph here was going along the z-axis. Okay, so in terms of doing this sketch quick and dirty, like if you have a problem and you want to find a volume or something, I want you to look and you go, oh, I have an x squared, a y squared, and a z squared. The odd guy, I only have one minus sign, so it's going to be a hyperboloid of one sheet, which means it's going to be going along the z-axis. And this is coming down like this, and it's opening up like that, like a tube. And right here, you have an ellipse. Let's put it on the maple for you to see it a little bit better. Okay. All right, the equation was x squared divided by 9 plus y squared minus z squared divided by 4 equals 1. Now I'm going to just let x range from -4 to 4. I'm going to let y range from -4 to 4. And why don't we let z range from -10 to 10? Tell it to graph it. Whoop. It's telling me I'm missing, now let's see, comma here instead. Okay, so I've got x equals ... Oh, here's a mistake. It's y equals. Y equals -4 to 4. Z equals -10 to 10. All right, let's click on it. I'm going to put an axis there. And you see? Now, Maple is not doing the best job at graphing it because it's cutting it and it's not showing the tube as well. So let's just make it go from -5 to 5. See if maybe I made my y's. That's a little bit better. Okay, and you can see it's a tube, and if we wanted to put the axes in there, okay, and as you can see, as you can cut it, you're getting your different hyperbolas as you cut it. Okay, before we do another one, let me actually do one just like this coming back. Let me make an equation up. What if I had x squared minus y squared plus z squared equals 1? Notice z equals 0 would be a hyperbola. X equals 0 would be a hyperbola. Okay. If you let y be 0, you have an ellipse. Okay. So seeing that it's x squared minus y squared plus z squared, I know I'm going to get a hyperboloid. Who's the odd guy out? The odd guy out, the 1 minus sign, goes with the y-axis. And so this is going to be a hyperboloid that's going to be along the y-axis. along the y-axis, along the y-axis, and it's going to be going like this. And notice as you slice it perpendicular to the y-axis, each time you slice it, if you take y equal to some number, you're going to get x squared plus z squared equals 1 plus y squared. This is some positive number for each y that you pick, and what do you have here? You're going to have a circle. And as we slice it perpendicular to the y-axis, we're going to get little circles. Okay, we have one more we've got to look at. This one, notice the equation looks very similar to what we had a few minutes ago, but notice what do we have? We have two minus signs. And this is called, in a few minutes you'll find that when you have two minus signs, notice if you let z be 0, you get a hyperbola. If you let y be 0, you get a hyperbola. Okay? And if you let x be 0, you're going to get nothing. Okay, and we'll talk about that in a minute. So let's do a couple slices first. Let's let z be 0. Okay, let's let z be 0. If I let z be 0, look what I get here. I get x squared over 9 minus y squared equals 1. What is that? That's a hyperbola. So in the xy plane, when z is 0, I'm getting a hyperbola at plus or minus 3. 1, 2, 3. 1, 2, 3. We are in the xy plane. xy plane. Okay. And in the xy plane, we're getting a hyperbola that's crossing the x-axis. Okay. Now let's do another one. Why don't we let z be 0. Why don't we let y be 0? So letting y be 0, we're in the xz plane. What do we get? We get x squared over 9 minus z squared over 4 equals 1. That also is a hyperbola. What axis is it crossing? The x-axis. So in the xz plane, notice the z-axis comes down here, we're getting another hyperbola that's coming like this and down. Up, maybe from this height, and down. We have two hyperbolas. And you're like, oh, I can't see the picture just yet, Mrs. Strocko. Now, this one's going to drive us a little bit nuts. Let's let x be 0. I'm looking at the yz plane. Notice if I let x be 0, I get minus y squared minus z squared over 4 equals 1. Notice if you multiply through by a minus sign, you get y squared plus z squared over 4 equals negative 1. Can you have a positive plus a positive to equal a negative 1? Can't happen. In other words, this graph has no points in the yz plane. There's nothing there in the middle in the yz plane. Let's see why. Notice, since x equals 0 doesn't work, I'm going to try other x's. Notice if I take this equation, I'm going to leave the x on this side, and I'm going to put the y squared and the z squared over 4 on this side. So in other words, I have y squared plus z squared over 4 equals x squared over 9 minus 1. Notice this side is always positive. It's always positive. Now, if that's always positive, this side has to be positive, right? What does x have to be for this thing to be positive? It has to be bigger than or equal to 3, huh? Or less than or equal to negative 3, right? Because you've got to have 3 squared over 9 to get 1. So when you subtract, you have to be bigger than that, right? So your x has to be bigger than or equal to 3 or less than or equal to negative 3. Well, going back here, you're going to have, here's 3, so I've got to be 3 or bigger or negative 3 or less. So my graph's only going to be here and here. Now, notice if I take any number bigger than 3 in here, and this turns out to be some positive number, what's y? So I'm slicing it along x equals some number bigger than 3. You with me along here? Like maybe x equals 4 or x equals 5. If you have y squared plus z squared over 4 equals some positive number, what shape's that going to be? An ellipse. So if I cut this, if I slice this, for z equals 4 or 5, I'm getting an ellipse. If I slice it over here, I'm getting an ellipse. And do you see what you're getting here? You're getting these two separate little sheets. And what are they called? They're called a hyperboloid of two sheets. Now, since we've developed it, there's like, Mrs. Strocko, I don't want to do all these slices and dices. It's too much work. You know, I'm going to get a headache. Notice you had 1x squared and 2 minus signs. When you have 2 minus signs, you have 2 sheets. When you have 1 minus sign, you have 1 sheet. Also, in this equation, which axis is the odd man out? He's a minus, he's a minus, he's a plus. The odd guy out is the x-axis. And notice your hyperboloid is going along the x-axis. And as you slice it, you're getting a hyperbola this way. And when you slice it, you're getting a hyperbola this way, because the two different ways of cutting it in the yz, the xz are going to give you hyperboloids. So if you had x squared plus y squared, no, I want 2 minus signs. Minus x squared plus y squared minus z squared equals 1. 2 minus signs tell me it's going to be a hyperboloid of 2 sheets. Who's the odd guy out? The odd guy out is the y-axis. So this hyperboloid of 2 sheets is going to be along the y-axis. So it's going to be 1 here, 1 back here, and when you slice them, you're going to have your like the 2 different sections. Okay, moving right along. We got 1 more to do. Oh, let's look at this one. 2 more. I lied. I have 2 I have to do, and then we'll do 2 exercises real quick. All right, this one right here. X squared over 4 plus y squared over 9 minus z squared equals 0. Now notice, if instead I had this, not 0, that would be a hyperboloid. But it's a hyperboloid of how many sheets? 1 sheet. It's going to be along what axis? It's going to be along the z-axis. Notice, if I let z be 0, what is this? X squared over 4 plus y squared over 9 equals 1. That's an ellipse. You get an ellipse. But it's along the z-axis, so you're going to have these hyperbolas coming down like this. You even have, you know, if you want to draw on the other axis, you can. And that's what that's going to look like. That's with equals 1. With equals 0, all bets are off. Now let me show you what happens when you have equals 0. Let's try cutting it up a little bit. Let's let z be 0. If z is 0, I have x squared over 4 plus y squared over 9 equals 0. What is that? It's a circle of radius 0. It's a point. It's the point 0, 0. So if you want to look at the xy plane where it's crossing the xy plane, it's crossing the xy plane right here. That's it. Okay? Let's try cutting it up. What if I wanted to look at a different height, like z equals 5 or z equals 10? If I took it a different height, let's try like z equals 5. Notice you have x squared over 4 plus y squared over 9 minus 25 equals 0. Or you could write that as x squared over 4 plus y squared over 9 equals 25. Just roughly, what sketch is that going to look like? It's a what? X squared plus y squared equals positive number. It's an ellipse. So if I want to slice it at z equals 5, I'm getting some kind of an ellipse up here. And there was nothing special about that z equals 5. Z equals 10 would have given me another ellipse. Okay, so as I slice it, or if I went down here and tried z equals negative 5, who cares? If you square a negative 5, you're going to get a 25. You're going to get some kind of an ellipse down here. So we're getting these ellipses, all right? Now, let's try something else. We tried the slice with z equal to 0. Let's try x equals 0. Now, when I do x equals 0, that's giving me the y-z plane, right? I'm in the y-z plane. If x is 0, I get y squared over 9 minus z squared equals 0. Or y squared over 9 equals z squared. What is that a graph of? Let's take the square root. If I take the square root of both sides, I get y over 3 equals z, or y over 3 equals minus z. What are those graphs of? What's the graph y over 3 equals z a graph of? A what? A line. That's a line. That's another line. Y over 3 equals z. Let's see, I already know these are my guides. Let's see. Y. What you're getting here, straight line. What does that look like? What is that? It's a cone. It's a cone. We just let x be 0, if we let y be 0, you're still going to get x squared over 4 minus z squared equals 0. You're going to get x over 2 equals plus or minus z. You're going to get a line. So when you get that equals 0 guy, you're getting a cone. Now, I could say when you have one minus sign, you've got a cone, but guys, if I multiply through by minus here, I'd have minus x squared minus y squared plus z squared equals 0, and I'd have two minus signs. So it's going to be one minus sign and two pluses, or two minus signs and one plus. But notice, who was the odd guy out? The odd guy out was z, and notice my cone's going along the z-axis, which helps so much. Okay, and as you look on this little cheat sheet that your book was so nice to give you, here they have the thing for the cone. But they only do it for z squared equals x squared. Notice, let me change my equation just a little bit. What if instead I had x squared minus y squared plus z squared equals 0? What's that going to be a graph of? It's going to be a cone, but it's going to be along the y-axis, absolutely. Along the y-axis, so you'll have it coming like this, coming like that, and here's your cone. Okay, all right. This is the hardest one to draw, and I don't do a really good job doing it. Z equals x squared minus y squared. I usually don't put this on the test for you to draw. I'll make it a matching because it's hard for students. It's very hard to draw, but we're going to try anyway. All right? Let's first let z be 0. Notice, if z is 0, we're in the xy plane, I have 0 equals x squared minus y squared, or I have x squared equals y squared. Take the square root of both sides, y equals plus or minus x. So I'm just getting two lines. Okay, and I'm going to do them in pencil. Y equals x. Oh, I don't like that pencil. Oh, the only pencil I brought was a red one. Well, that's no good. Oh well, we'll deal with it. We're going to go, it's just two straight lines, like one going like this and one going like that. I'm not going to put them in. Now, let's let y be 0. If I let y be 0, okay, so if y, this is x, y, z. All right, so if I let y be 0, I'm in the xz plane. What do I get? Z equals x squared. You guys know what z equals x squared looks like, right? It's a parabola. Comes down like this, and comes back up. Now notice, if we let x be 0, we are going to get z equals minus y squared. So if this is the z-axis, this is the y-axis, which way is this parabola going? Down. So in the yz plane, we have a parabola that's going this way. Okay, you see that? This is in the xz plane, this is in the yz plane. Okay, now, notice, for z equals 0, we had two straight lines. But why don't we try, let's try slicing it some positive z. You know, I want to cut it up along here and see what do I get if I cut it along here. Maybe z equals 5 or z equals 10. Well, notice if z is some positive number, z some positive number, I have some positive number equals x squared minus y squared. Like if z is 5, I'd have x squared minus y squared equals 5. What is that? Hyperbola. That's why we reviewed them. It's a hyperbola. It's a hyperbola that's crossing what axes? The x-axis. Ah, this is my x-axis raised above. So I get this hyperbola, and we're going to have one. Oh, he has to come all the way back here, and I have, whoop, that should be dotted, I apologize. Okay. Now notice, if you come down with z negative, if you let z be negative, like maybe it's a -5, notice if you multiply through by a minus, you'd get 5 equals y squared minus x squared. You see, because I multiplied through by a negative. This hyperbola is going to be crossing the, it's changing. So down below here, you're going to have your hyperbolas going like this. So it's something that you have your hyperbolas, when you hit the xy axis, you get these lines, and then the hyperbolas change which axis they're doing. It's looking like a saddle is what it looks like. You see, because you've got this one parabola here, and you've got the hyperbolas here, and as you get bigger and bigger, they get further and further apart. But when you come down here to the xy axis, you're actually getting, the hyperbolas are feeding into these straight lines. And then when you get below the xy plane, the hyperbolas are coming in this direction instead of that direction. Let's put this one on maple. I think this would be helpful to look at maple. All right, I'm going to do, in fact, let's just do it right here. Let's make it be z equals x squared minus y squared. Now, if you're thinking, am I going to use this stuff this semester? Absolutely, guys. We're going to be finding the surface areas of these suckers, the volumes of them, all kinds of neat stuff. Here is my, let me put an axis around him. Do you see? There's the parabola we were talking about. Here's the hyperbolas when we're crossing it for different z's. But notice, above the xy plane, your hyperbolas are going this way. The negatives, do you notice they're going in the opposite direction? The hardest thing to draw. I mean, it's a real art form to draw those. What is this thing called? He is called a hyperbolic paraboloid. Because here is your parabolas, and here's your hyperbolas. Pretty cool. Okay. All right, I want to go over a couple. Just a couple. I think we did enough. All right, but we're going to practice just a little bit. What if I want to sketch z equals 4 minus x squared? Sketch the surface. Z equals 4 minus x squared. Now, first of all, cheat for a second. Go in the xy plane. And say to yourself, what does z equals 4 minus x squared look like in the xy plane? You can put it on your calculator. If you put it on your calculator, you'll see it's going up to, it's a parabola that's going down z. It's a down z, right? That's what that is in the xz plane. But now in 3D, notice, is there a y coordinate there? No. So what we're going to do is we're going to sketch it in the xz plane. It was a parabola that went up to 4 and then down. And notice it goes forever, but I'm going to stop it. Since there's no y, we're going to drag it along the y-axis. And what I do is I just draw another axis and then draw the exact same thing. And then show this point's getting drug, this point's getting drug, this point's getting drug, this point's getting drug. And do you see the sheet that you have going around like that? Okay, and that's what it looks like. This is called a cylinder. Whenever you're dragging it, that you're missing one of the coordinates and you're just dragging along an axis, you're called a cylinder. Okay, let's do another one. Sketch the region bounded by the paraboloids z equals x squared plus y squared and z equals 2 minus x squared minus y squared. Okay, first of all, let's do each of them separately. Looking at z equals x squared plus y squared, just doing that one separately. Notice, for various values of z, for positive z, this is a circle, right? For different values of z equals, you're going to get x squared plus y squared equals a positive, and you're going to be getting a circle up there. When z is 0, you have a point. If I let x be 0, I get z equals y squared, which is a parabola. If I let y be 0, I get z equals x squared, which is another parabola. And so it's going to be looking like this. It's called a paraboloid. Going up. Now the other guy, let's do him next, and then we'll put them together in one graph. The other guy z equals 2 minus x squared minus y squared. Notice if you let z be 0, you get 0 equals 2 minus x squared minus y squared, or x squared plus y squared equals 2. What is that? That's a circle of radius square root of 2. So down here we have a circle of radius square root of 2. Okay? Notice, what if I let x be 0? If I let x be 0, I get z equals 2 minus y squared. In the yz plane, what does that look like? It's a parabola that's a down z that's going up to 2, right? So in the yz plane, I'm getting this parabola that's coming down like this. Now what if I go into I just let x be 0, so let's y be 0. If I let y be 0, I get z equals 2 minus x squared. Again, in 2D, that looks like that. So in here, okay, now I'm going to cut it a little bit yet. Since we have z equals 2 minus x squared minus y squared, if I let z equal to some positive number, I'll have z minus 2 equals minus x squared minus y squared. Or if I multiply through by a negative, minus z plus 2 equals x squared plus y squared. Well, this is a circle as long as this is positive. And that's positive as long as z is not bigger than 2. So I'm going to get circles until I get to z equals 2. Circles, circles. And when I hit z equals 2, it ends. And so this is a paraboloid that's going down is what it's doing. So if I wanted to draw the two together, this one's going up forever. This one's upside down and starting at 2. I wanted to sketch the two of them together. The one's going up like this. And the other one's starting at 2 and going down. And it goes down forever, but if we want the intersection of the two, it's going to look something like that, sort of like a skewed kind of egg. Okay, now before we quit, I actually put this in your homework, but we're going to do it together right now. Numbers 21 to 28. All right, 21 to 28. They have the equations, and they want us to match. Now, don't frantically copy this down. Well, maybe you want to do it for the evens, though, because they aren't in the back of the book. I forgot about that. Maybe I'll post that back on Blackboard for you. But they want us to match the equations with the graphs. Now, let's look at the first equation. The first equation is x squared plus 4y squared plus 9z squared equals 1. That's 21. And 22 is 9x squared plus 4y squared plus z squared equals 1. What are those graphs of? They're both graphs of ellipsoids. No matter how you dice them, or you should get real comfortable. The ellipsoid's your easiest. It's x squared plus y squared plus z squared. X squared plus y squared plus z squared. They're both ellipsoids, but now there's going to be two for us to choose from. Let's find our ellipsoids here. I have one here, and I have one here. You see the two right there? Which one is it? All right, now looking at 21, if you let y and z be 0, let y be 0 and z be 0, what does x have to be? Plus or minus 1. All right, if you let x be 0 and y be 0, x be 0 and z be 0, you have 4y squared equals 1. So y is going to be what, plus or minus a half? And if I let z be 0, x be 0, y be 0, I have 9z squared is 1, so z would be plus or minus a third. So you can see this ellipsoid's fatter in the x direction than it is in the y direction and the z direction. That guy's fatter in the x direction than he is in the y or the z direction. I bet you he's 21. Looking at this guy, if you let y and z be 0, x is plus or minus a third. If you let x and z be 0, y is plus or minus a half. If you let x and y be 0, z is plus or minus 1. He's fatter in the z direction. Definitely, he's fatter in the z direction. 22. Okay, now cones. I have a cone right here. Cone, well, let's not do the cone. Let's do this guy first. That's a hyperboloid of one sheet. That's going to have an x squared, a y squared, a z squared, but how many minus signs? 1. And since this is going along the y-axis, the minus sign is going to be with y. So let's find one. Right here he is. X squared minus y squared plus z squared equals 1. Hyperboloid of one sheet going along the y-axis. That's going to be 23 for sure. That's a hyperboloid of two sheets. So he's going to have two minus signs. And he's going along the y-axis, right? So the odd guy out is going to be the y. Now since you have two minus signs, that would mean the y would be a plus. So looking right here, 24. All right. This guy's a cone. The cone has equals 0. I don't see an equal 0 though, do you? But looking at this baby cakes, this would be 0 equals x squared plus 2z squared minus y squared, right? The odd guy out is the y, and we have equals 0. 26 is going to be the cone. Okay, so what we have left, which ones haven't we done yet? We haven't done 25 or 27, all right? Oh, or 28. Okay. The bizarre guy, which is the one that looks like a saddle, the hyperbolic paraboloid, 28, that's going to be this guy. What's this guy going to be? Let's look at him. X squared plus 2z squared equals 1. Just in the xz plane, what's that a graph of? Just in the xz plane, what's that a graph of? It's an ellipse. So if I put my ellipse here, drag it along the y-axis, what am I getting? A cylinder. Aha, there he is. There he is. So this one here is 27, and by default, the only one I haven't done yet is 25, so he would be there. Okay, so I just went over them, but I want you to go over them again. All right, for homework for next time, I want you to read pages, and the textbook does a nice job. You really do want to look over their examples. You want to read pages 868 to 873. And then on pages 873 to 874, I want you to do 1 through 7, the odds. And 11 to 19, the odds, they tell you to do all these traces. All I care about is can you identify it and sketch the surface. And then 21 to 27, I want you to do them all. That's that matching that we just did. All right, and I'll see you next time for our last section.